All right, I'll begin with a word of prayer. Heavenly Father, we thank you for this time we have just to meet together and study your creation. Just pray you would glorify, you be glorified in what we do today, Lord. In Him I pray. Amen. I keep saying this today. I don't know what's wrong with me. Anyway, all right. Questions?
Yeah, so this is a mission question.
I don't know. It's fine.
3.4, number 35 and 36.
But you probably have questions about like typos. Those I will consider.
So
30 what?
35 and 36. It's just the part C's on like those.
Now in 35 part C, he says if R is a division ring, show that R adjoin N has three ideals: 0, Rn, and R. R is wrong. Yeah. So R adjoin eta, let's say, has ideals 0, right? R times eta, and also what? I lost my place. Yeah, and R, exactly, and the whole thing. Which he writes, and I refuse to write, with not square brackets. Because, well, here's why that would, I mean, this, no, wrong. No. But yeah, that's a typo. That R is supposed to be R adjoin omega. And I'm sorry, I've been aware of this for a little bit. I should have sent an email out about that. But anyway, now it has been officially announced. 35C typo. Any other?
And then 36C, can you just like verify the notation on that one as well? Like the R and then parentheses 1 plus gamma, is that multiplied by or is that adjoined?
Yeah, that's why this notation is
Yeah.
What a simple.
I'm guessing that's it.
36, right?
Yes.
I actually worked out part B in class. It's funny. Of course, I called gamma J. You realize that this R adjoin gamma is really the hyperbolic numbers, right?
Yeah.
So you're wondering for part C what? C or B that you're worried about?
C with the R parentheses 1 plus gamma and R parentheses 1 minus gamma, is that adjoin or multiply?
Son of a gun, I worked your homework in class. Dang it. I did not mean to do that. Man.
That is true.
Yeah, I didn't even look at the
We get very
notes.
familiar with it.
Yeah, 35B is pretty, I mean, it's similar.
Yeah, and this is, hey, you know what? This is another, well, but no, the middle, the R times 1 plus gamma and R times 1 minus gamma, that's, you know, you could, you could equal for number 36. Again, section 3.4. R times 1 plus gamma, you could equally well express as this, meaning that it is the set of 1 plus gamma times R such that R is an R, right? Yeah. Oh, actually, this is not quite what I did. What I did in class, see, this is, what is R here? He doesn't even say in problem 35 at the start. There may be there. Oh, you know, in his defense on page 196, at the very beginning, the preamble of these exercises, it says throughout these exercises, R denotes a ring unless otherwise specified. So there you go. R is a ring. So yeah.
And he points you back to page 172,
Uh,
where a lot of this is discussed.
That is also true, yeah. Of course, what I did in class, I assumed R was the real numbers. So I was wrong. These are not hyperbolic numbers. These are like the hyperbolic numbers over a ring. They are the hyperbolic numbers in the case R is equal to the real numbers. But yeah, in short, I think you're right. The last R should be R adjoin gamma, but the other two are just multiplication by gamma, plus 1 or gamma minus 1, 1 minus gamma. Yeah.
How would you go about showing, like, I know how you show that they are identicals. How would you go about showing that there are no more?
Oh, I think it's actually Zach's question.
What?
Zach asked me a question about, he was trying to ask, like, don't any two ideals have to be perpendicular or something like that? And then I stumbled upon the comment that if you pick anything that's not of the, I mean, basically the point is the zero divisors of R adjoin eta are exactly, you can prove this, you know, a plus b eta such that a squared is equal to b squared, right? Those are the zero, I mean, anything of that form is a zero divisor because, you know, if you have a plus a eta, you can multiply that by a minus a eta, and you'll get, excuse me, a squared, 1 plus eta times 1 minus eta, also known as 0. And likewise, if you have a minus a, I mean, actually this kind of shows you both this thing and that thing, they're 0. The other, you might call them nil factors or something. They're both zero divisors by this calculation. What about anything else? You can show anything else. You can actually show that 1 over, in some sense, I mean, this is a bad, let me write it in, you can show a plus b eta inverse is equal to, but that's why it's a division ring, right? Yeah, that's why you need a division ring. So this would be a
inverse minus a inverse.
You can prove that. So what's that mean? I mean, in other words, right? If you have, suppose J is an ideal, right? Is a subset of R adjoin omega, right? Then if J contains point not in, you know, R times 1 plus gamma union R times 1 minus gamma, right?
Wait, are we in the gamma one or the eta one?
Oh, I'm sorry, where am I? That's a good question.
I mean, the only difference is gamma squared is 1 and eta squared is 0.
Oh, I'm sorry.
That's the only difference. So it's
That
just-
matters. This is supposed to be gamma. I'm sorry, guys. I warned you I would do things. Gamma, 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 gamma. Gamma, 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 gamma. Gamma, 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 oh, gamma. Gamma, 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 oh, gamma, 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 gamma. Gamma, 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 gamma. Oh, no, that was from previous problem. Okay, good. The point is, if you take an ideal, any other ideal, right? If it's another ideal, which is not one of these guys, right? That means it contains a point outside of those guys. But that means it has a unit. But any ideal which has a unit is the whole thing. And then, of course, you have the zero ideal inside these two as well, right? Those intersect at the zero ideal. And the intersection of two ideals is an ideal. So you got zero, you got this one, you got that one, you got the whole thing. For 36 anyway. And I almost gave you that in class the other day. But admittedly, I did it with J, and you might have disregarded it as it was a question from a certain student. So, I don't know. I know when I was lost in a class and a particularly bright student asked a question, sometimes I'd just be like, whatever.
That's the time I used to go back over the board and try to catch up.
Yeah, there's a 50-50 chance the question is about something that's really interesting and deep, as opposed to it being about me writing zero without a hat on it or something. You know, I mean, you never. But attention to detail is what leads to success in here. You know, it's good. And yes, doing homework is the. As the student from Dr. Skambordis' physics class a few years ago complained, other students are cheating. They're not just doing the homework you assigned, they're doing all the problems at the end of the chapter. And that student wasn't joking either. He was actually serious, and I was like, wow, that's special.
No, you're not allowed to do it anymore.
Skambordis runs into some interesting stuff from time to time. I often wonder if he actually says the thing he says to students. I don't know if I believe it sometimes. If he actually says some of these things, it's hilarious.
He does.
Oh, he does? Okay. It's amazing. Anyway, you have other questions?
Maybe not an answer legally.
Legally?
There was also, and this you guys may have already turned this one in, but maybe on the previous homework there was a Z that was supposed to not have a double Z on it. Was that from mission 7?
Yeah, I think Sam pointed that out.
Sam shared the wealth there. That's good, yeah. If I had more energy, I would email about all of these things, but anyway, that's history. So at some point, I'll publish a solution to that.
Do you have any questions?
I don't think so. The rest of it.
Yeah. I mean, do you remember the one we did last help session where you ended at the end and couldn't figure it out? That's probably the only question I still have. So if you want to try, but we can just go over the test.
What about training?
We'll try it. Let's try it again. I give myself 5 minutes.
Okay.
What one was it?
3.3, number 8.
All right. This feels bad. Number 18?
Yes.
It looks.
Part B of it. We
but
figured
it-
out part A.
Oh. Number 18, section 3.3?
Yes.
All right. Ba-dum. We have A, B, C ideals. Of a ring R. And we have A is a subset of B. And we also have that A is a subset of C. And we're supposed to show that, where was I? B over A.
Intersect C over A.
Okay.
Is equal to B intersect C over A. And the same thing for addition instead of intersection.
All right. All right, first of all, I'm going to draw a picture that may be helpful to me, possibly. So we've got, B and C are in no way related, except that this is B, this is C, and A is in here somewhere, right? And we know 0 is in here, because they're all ideals, so 0's in there. All right. So which one do you want to, guys, which one should we try to attack first? The addition or the intersection? What do you want? Intersection? All right. Here goes. B plus A is an element of B over A intersect C over A. Implies, let me say, I'm going to leave that B. I'm going to put that B. At least I have that much. Of course, B plus A is an element of B over A, and B plus A is an element of C over A. Right? Now this means that B is an element of B, and this means that B is an element of C. So B is an element of B intersect C, which means that, yeah, B plus A is an element of B intersect C over A. So therefore, B over A intersect C over A is a subset of B intersect C over A. I feel like this idea right here may have been absent from my previous attempt. This understanding that if you have something that is in the coset space of C over A, that means the representative has to be somewhere in C. I'm not sure I did that last time.
I think last time you let x equal b plus a, and so that's why you couldn't see it, is because you reduced it to just like...
Yeah, but I feel like that's my, if I had to play blame game here. Now, on the other hand, if we have b plus a is an element of b intersect c, okay, it's almost the same argument. B intersect A, then that implies that B is an element of B intersect C, which means that B is an element of B, and B is an element of C, which implies that B plus A is an element of B over A, and B plus A is an element of B, C over A, rather. So therefore, B plus A is an element of B over A. Intersect C over A. Okay, there we got it. So there's the other. You're right. I think you're right, Chris. We could make them. We could just reverse the inclusions. I'm just scared, given my previous experience with this problem. I have a certain cowardice, and it's not a logical one, but it's there. Okay, the other one then. We'll try the other one?
Yeah.
Okay, so if we have x an element of b over a plus c over a, then that implies that x is equal to b over a. Oh, I'm sorry. Goodness gracious. No. X is equal to b plus a plus c plus a for some b plus a in b mod a and c plus a in c mod a, right? That's what we mean. That's how the sum of two ideals is defined. It's the addition of one thing in one and one thing in the other, but that, of course, is equal to b plus c plus a. How do I know that? Well, that's how we define addition of cosets. Right? I mean, that's just a calculation in R mod A, right? So, but this is an element. This is in B plus C mod A as B is in B and C is in C, right? So,
B plus C is in B plus C.
right.
Yeah, you can just write that.
Little b plus little c is in.
Oh yeah, I'm sorry. I hadn't. You guys are finishing my thought. Thank you. Very good. Now, the reason I know this and that, it goes back to this means that B is in B, right? And this means that C is in C, little c, little b. And consequently, we got at least one direction. I bet we could just reverse the
Yeah.
implications here. Yeah.
I wasn't here for that last help session, but I'm not gonna watch. I'm curious.
Yeah, that just shows you that, like, sometimes you come here asking me a question assuming I have some ounce of mental capability, and that would be wrong because it's, nearly 6 o'clock on a Tuesday or Thursday, and sometimes I'm out of the juice, got no juice left. But I think this is okay, yeah. Another direction, gets the other inclusion, yeah.
Even if it's not the same, it'll be very similar to the intersection one.
Again, I think that I really feel like this is the thing I was not grasping.
This is helpful in general to understand how ideals work in elements, because it is different dealing with this type of mod.
Yeah, we had those right cosets in the factor group stuff. Now we've got this additive left coset.
Makes for a fun one. If you put the questions right next to each other.
Ooh,
So if you have ideas.
how can I confuse the students maximally? It's like you can make a final where no one got any points. It would be the perfect final. My advisor once told me that it's not grading unless you take off points. So, yeah. I'm just looking at number 12, part E in section 3.3. Show that the annihilator of x is the annihilator of the annihilator of the annihilator of x.
That was a mission problem.
Yes.
Yes.
Oh, cool.
And slightly
I called it banana in my mission because I got really tired of writing.
It does. It does look like banana. Just add a B to it. Banana. What time is it? All right, let's let's just go over the test for the rest of the time. That will get it out of my system. The projector's actually working today. Let us not tempt the fates. I'm somewhat cogent at the moment, so although it seems kind of like a waste to not try more homework, but anyway. All right, where was I? Your solution you'd like to. See if I can find my laser. Yo. You got it in frame, Peter? Okay. I'll make it bigger. Still good? Okay, so let's see here. Let me begin my ranting. Problem number 1. Find the order of k plus 2 in G mod k. This means the order of this coset as an element. It does not mean to tell me that there are 4 things in k. Anyway, sorry. So if you just add it to itself, you'll see that you don't get back where you started until you get to 5 times itself, which brings you back to k again. So it has order 5 as an additive coset. So that was the one. A lot of people got that wrong. Oh my goodness, so many people. Number 2. You can interrupt if you have questions at any point, okay? Otherwise, I will just forge ahead. Here, this is the center of D4, which we've played with a fair amount. We know that's a normal subgroup from our previous experience. Anyway, so that's normal. And so the factor group is meaningful. Given that the order of the dihedral group, this is the octet group, right? It's got order 8. And the center has order 2. We expect 4 elements in the coset, the factor group rather. And here they are, k, ka, kub, and kaba. And as you can see, we get k, 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 and k, k, kaba, kebab, and so forth. And if you look at this, you can kind of recognize this is the Klein 4 group, right? Like you see these, the pattern is it's very Klein 4-ish. The point is, each one of these has order 2. They all square to 1, which in this context is k. And so anyway, there it is. Criticism I have of the class, people spent a long time on this problem, like way, way more than you should have, because you did not recognize that this was not normal, and so you calculated a KLA table here. That's a costly mistake in terms of time. And some people had like an 8 by 8. I don't even know what that is. But what's done is done. But the point here is that if you calculate BK versus KB, they're different because this is not a normal subgroup. In fact, I think I might have done it with D3, but it's a pretty similar situation. Number 3. So, yeah, you guys got away with a lot here. This was the kind of argument I wanted to see. Suppose HA is equal to HB, then 1 is in H. So that means that 1 times A is in HA. In other words, that A is in HB as well, since they're equal, right? Thus, there exists H in H such that A is equal to HB, and so we find that AB inverse is equal to H, which is in H. What I, by and large, saw people do was take this and multiply by B inverse on both sides, as if that's somehow meaningful. I didn't take points off for this because I can understand how you thought that was meaningful. But there's a lot of people who didn't lose points here who will lose points when I re-ask the problem with more careful wording on my part. The more careful wording on my part will be, prove this, if and only if this, by a careful point-wise examination of the proposition. All right? Because you should be able to furnish these kinds of arguments, and most of you did not. But I felt bad because my wording wasn't clear enough, so I didn't take up points. Now, some of you just wrote stuff that was wrong, so I still take up points, but that's another thing. Anyway, In the other direction, it's a little bit subtle, actually. If you suppose that this is in H, that means that there exists an H such that that's true, right? And conversely, that's true. And so ha is, we could write as H bar A, such that H bar is an H. Well, then that would be H bar H inverse A, but H inverse A is B, so you got H bar H B for arbitrary H. And then I actually need to do a little argument to explain to you that that is actually the same as HB, because as H bar H runs over all choices of H bar, that hits everything in the group. Here's the proof. Because if you pick anything in the group, say X, then you can select H bar equals to XH inverse, and that will give you that HH bar is actually back equal to X again. This is, I think, a complete solution. Now, the way I proved it in class or in the book was a little bit different. This is the proof I thought of it when I was writing the solution, so whatever. You'll find a slightly different argument for this part of it if you look in the book or in the lecture. Find all homomorphisms from D3 to Z7. All right, so this was supposed to be a gift, but it was not a gift which was freely taken. It was a gift that was refused. Categorically refused by many, many students, and that's unfortunate. This is something that was supposed to be whited out, I believe. I don't know what this is. This is some kind of Hebrew letter or something? I'm not sure what that is. Anyway, if you have a homomorphism from D3 to Z7, then you need some different things. First of all, you need that the order of the image divides the order of the target space, which is Z7 here. Which means that your images have to have order 1 or 7. Them's your choices. On the other hand, D3 is generated by A and B, A order 3, B order 2, such that they play like so. And there was some, I wonder what this word was supposed to be. I feel like there's a word missing here. I don't know what I did. Maybe therefore and, or maybe just, that was supposed to. Thus, and I'm not sure what, there's a grammatical problem right here. Minus a half. Let's see here. I'm not quite there in my grading just yet, but so if you have phi of A, but whatever you do to phi of A and phi of B, that fixes the action for the homomorphism, right? But on the other hand, the other thing we know is that the order of the image must divide the order of the pre-image. So that means that this has to divide that, and that has to, so in other words, phi of A has to divide 3, and phi of B has to divide 2. But the thing is, 2 and 7 and 3 and 7 are relatively prime, so that forces us to send everything to order 1. In other words, we have to map everything to 0, only the trivial homomorphism exists. So there's that. A lot of people got problem 5. That's great. That shows me you're studying. Yay. And that made me happy. It would have made me more happy if about 5 of you had actually written this down as opposed to burying me under a paragraph of blathering. Sorry, but like this equation should appear somewhere. It's kind of the heart of the matter. Some of you guys discovered this formula in the paragraph about prime factorizations and divisibility, and like, I think you're right, so I didn't take off a lot, but I might have taken off a point because it was just not clear. Proofs should be clear, that's part of it. So if I have to work too hard to understand your proof, there's probably something wrong with it. You could argue there's something wrong with me. I sometimes can't argue. I mean, you might be right. If you feel strongly about your proof being more awesome than I realized, feel free to come talk to me about it. Anyway, so this is basically the thing, is that since this is equal to that, which is equal to this, which is equal to that, if this is P, that means this is 1 and that's P, or this is P and that's 1. And those two cases either give us that G, the H is equal to K, or that G is equal to H, which is what we're trying to prove. By the way, this was example 6 in section 2.6 of Nicholson, which I did cover in class at a somewhat reasonable speed, I think. I believe this was also an example I covered in class. I don't remember for sure if I did this or not. It's definitely something you should have read and studied at a minimum. Anyway, this is Theorem 2 in section 2.9 of Nicholson. And the proof goes like this. You take a subgroup of the center And we're assuming that the factor group by it is normal, cyclic. Of course, K has to be normal. The fact that it's normal follows from the fact that it's a subgroup of Z of G, right? Anyway, so choose A and B and G. My goal is to show that A times B is equal to B times A, right? I want to show that G is abelian. First of all, there exists M and N and Z such that Ka is equal to that and Kb is equal to that because, again, G mod K is cyclic, so it has a generator Kx. So there has to exist an integer m and integer n such that Kx to the m and Kx to the n is equal to Ka Kb. But what that means, of course, is that there exists K1 and K2 in K such that Ax to the m inverses K1 and Bx to the n inverses K2. Which is to say that A is equal to K1x to the m and B is equal to K2x to the n. All right, thus calculate. AB is this, right? But remember that K2 is in the center because it's a subset of the center, which means that K2 commutes with K1x to the, can't read, m. Sad, m. And so I move the K2 over there. And then what do? Well, these commute because laws of exponents, and right? So I can switch mn to nm like so, and then I move the, what else do I do? Oh, then I commute K1 and x to the n because, again, K1's in the center, but that's exactly B times A, which shows you that since A and B were arbitrary, that the group is abelian. Well,
this is the one Devin was asking.
yeah, yeah.
The same thing he did.
Definitely. Well, I guess my main criticism is that many people do not have the K here, which is kind of important. And this is definitely supposed to be 1 in the factor group, right? And I think there's an error in my solution. I really should write, I think I should just write K here, right? And so if you had K here and I took off a point, I should probably get that point back to you. I agree. There may be a couple of you like that. Now if you, well, anyway, let me not blather on about that. This is, of course, the correspondence theorem. And there it is. The dreaded problem 8. So, yeah. Basically, what you want, so I fixed it because, well, it's, I'm not sure this is actually true. Anyway, I have proof for the latter case. If we look at positive determinant matrices, that is definitely isomorphic to the positive reals direct product with SLN. Here's the isomorphism. We'll just take the determinant of A. That gives me a positive number by construction. And then I need to have the 1 over the nth root of the determinant of A, multiplying A over here. The reason I need that is when I take the determinant of the second factor, and here's the thing you guys didn't remember from linear or wherever, is that when we pull a constant outside of a matrix, when we take the determinant of a 3 by 3 matrix and you pull C out, you pull out C cubed. For a 2 by 2 matrix, if you have C times A, the determinant of CA is C squared times determinant of A. It's the constant to the order of the matrix that you pull out of a determinant. This is a not so appreciated fact in this class. Let's see here. So, like, I don't think anybody had that. Maybe that's my fault. I taught linear to you guys. Like, it's probably my fault. Still gonna take out the points though. Let's see here. So 1 over, sorry, too soon? No. Anyway, 1 over, so this works out to 1 over determinant, and of course if this is positive, they cancel and they give you 1, which is good because that's what we need for this to be an SLN, right? So the map is at least N2. And then here's the homomorphism property, phi of AB's, determinant this and that, but the determinant product is product of the determinants. And likewise here, and so I get this and that. Now when I, let's see here, right, but that is exactly phi of A, and that's phi of B, right? So there's a homomorphism property. Then to see that it's onto, if you pick alpha comma b in here, and you consider the determinant of the nth root of alpha times b, well, that gives you back alpha. So if I look at the nth root of alpha b, that's in G, because it's a positive determinant matrix. And so if I map phi of the nth root of alpha b, that gives me this comma that, which is exactly alpha comma b. Because here, when you calculate the determinant of this, you get words. Curses. I'm sorry, let me scroll down a bit. So the b sits out here by its lonesome, and this, when you calculate, you get determinant of b times this to the minus 1 over n power. I feel like I may have a typo here.
Where do you think you told me?
I don't see how this goes to that.
How the determinant, so you have the determinant of the
Oh,
you pull it out, so it's
oh, right.
to the minus 1.
Okay, thank you. I'm a victim of my own stupidity. All right, there we go. Anyway, likewise, it's easy to see the kernel is the identity, so it's a isomorphism that shows you half of the problem. Because I also tacked on show that SLN is a normal subgroup of GLN, because I had in my mind that this was a connected problem, but of course it's not. So problem 8 is actually 2 problems. Now what you should have done is glommed on to the easy part, which is to show that SLN is normal. That's 2 lines. Anyone could have done that in here. And a few people did, and I gave them half credit. Like, well, that wasn't me, so shut up. It's like, maybe it was you. I forget who it was, actually, but a few people.
We had looked at it like right before the test.
Ah, good. This was either homework or a proposition that I went over in class, I forget. But it's pretty straightforward. If you have H and K normal subgroups, the intersect is 1. You're supposed to prove that HK is KH, right? So I told you the hint is to study the commutator, right? And so we have these are normal subgroups, and if we look at K H inverse, well, that's in here, which is that, right? So this is equal to K1 by normality of K. In other words, the commutator of H and K is actually K1 times K, so that's in K again. But on the other hand, by the normality of H, we have that KH inverse K inverse is in H, which means there exists in H1 such that, right? So I can also find that the commutator is HH1, which is in H. So the commutator is both in H and in K, which intersect at 1, which thus proves that the commutator is exactly 1, which is to say that HK, H inverse K inverse is 1, which is tantamount to saying HK is equal to KH, but they're arbitrary, so that proves it. So sometimes my hints are not helpful. I feel like this hint was helpful if you followed it. I threw in a second proof for problem 8 because I didn't like my first. And the second proof, because somebody almost did this correctly, and this was, somebody had the insight to try to go the other way. Going the other way is a little bit nicer. Well, first of all, here's the proof that SLN is normal. Although this was not the proof you guys gave me. This is the proof everyone should give me because it's the easier proof. SLN is normal since the determinant is a group homomorphism from GLN to non-zero reals. Its kernel is SLN, and since the determinant is a group homomorphism, that proves that SLN is normal. This is the laziest and simplest way to prove that SLN is a normal subgroup. If you give me this argument and I say that you're wrong because you didn't put enough detail down, that means that I'm being a jerk. You should tell me that. But no one put this down. So, anyway, this one, the other way to do it would just be to take alpha beta and map it to alpha beta. Alpha B, rather. You can prove that that's a group homomorphism. The proof that it's a group homomorphism is obviously easier because you're not fussing with that nth root stuff, you know. And it's also easy to see that the kernel is that, so it's 1-to-1. And so up to that point, I was like, wow, this is way, way easier if you go the other way. There's no nth root in here at all. Like, what happened? What's going on? Well, then I tried shows onto, and then I realized, yeah, it's unavoidable. So to show theta's onto, I have to take A and G, and basically I want, if I put B equals to this, so the determinant of B is 1, then I can map theta of the nth root of the determinant of A times 1 over the nth root of the determinant of AA, and that will map to A, so it's onto. But at some point or another, you have to face the music, and you need to know that identity for the determinant, otherwise you can't really do this problem.
Just write
Clearly onto. Aha. When in doubt. Yeah, I won't figure that out. Of course, there is the chance that it's actually, if it does happen to be easy, you'll get away with it, right? That's not a bad strategy.
It's better than not.
But if it's not, now that will work with me. You gotta be a judge of your judge, you know. There are other professors, you try to do this, that it won't go well for you. I guess if I'm in the wrong mood, that might also be true, but anyway, I digress. All right, so you guys do not have a clear plan for calculating an isomorphism. You guys have to have a plan of action. The plan of action for finding an isomorphism if a formula is not apparent, right? If it's not something stupid that you can just read the formula. What you want to do is map generators to generators. So here, D6, it's got an element of order 6, right? It's got this A, which has order 6. And I'm claiming that it's isomorphic to S3 cross Z2. What has order 6 in S3 cross Z2? I think there are only two things. Sigma comma tau, and, excuse me. The one I chose, though, of course, was sigma 1. 1 has order 2 in Z2. Sigma has order 3. Least common multiple of 3 and 2 is 6. So this has to be where you map A to. You could also map it to sigma squared comma 1. Fine, but that'd be weird. And then sigma B, well, I figure it should be tau 0. Now, that's a guess, admittedly. Both of these are, this is an educated guess. There's really only two choices. And then I choose this. Then all I have to do, that defines phi, because I've defined it on the generating set. I just need to then check that it preserves the relation. If it does that, then it's an isomorphism. And here's the proof. If you look at this times that, well, that's this product, which is sigma tau sigma, 1 plus 0 plus 1, which is tau 0, which is sigma b. So as you can see, just like ABA is equal to B, phi of A, phi of B, phi of A is equal to phi of B. So the relation is preserved. And then counting completes the argument because they both have order 12, so that it follows it has to be onto and 1-to-1 and all that. Why can a group of order 26 not be simple? This was a theorem we had that a group of twice a prime order was isomorphic either to the cyclic group of order 2p or to D2p. Excuse me, DP, the dihedral group actually of order 2p. So if it has 26, it's either D13 or Z26 up to isomorphism. And both of these have subgroups which are normal and which are not the whole group. So they're not simple. That proves it. Now, you guys, many of you use the CeeLo theorems. More power to you. Fine, great. No need for it, though. We can rely on less elegant things to do this problem. This one here, show a group of order 40 cannot be simple. We worked that in here. This is one of the homework problems that was assigned, and we actually made sense of in here. You guys probably got it, right? Okay, good. But basically, it's CeeLo's third theorem. 40 is 5 times 2 cubed. So I need the number of CeeLo 2 subgroups is congruent to 1. I also need that the number of CeeLo 2 groups divides 5, which means n is either 1 or 5. Likewise, the number of CeeLo 5 groups has to, be 1 mod 5, and it has to divide 8. And so if you look at these equations, what are we forced to say? We're forced to say that the number of CeeLo 5 groups is 1, which means there's a unique CeeLo 5 subgroup, which is then necessarily normal by this CeeLo theory. And anybody understand my quote? No? Okay. Just checking. Problem 13. And I was very encouraged by this problem. Many of you were successful in proving that this does in fact define a group action, and you had good and complete details to affirm that. I was very happy, by and large, with the class. A lot of people were able to show at least that part of it correctly. I didn't really have anybody quite describe the orbits like I wanted. I mean, some people describe them as a point set. Great. That's not really what I'm asking. I want a description of them. And one of the things we learned in linear algebra was that if you look at, PA Q inverse, you can look at that as a change of coordinates where you're changing the base in the domain and changing the base in the range separately. And we had this rank nullity theorem, which said the appropriate choice of bases, you can transform your linear transformation so it's an identity matrix padded with zeros. The size of the identity is the rank of the map. So the answer is that the orbits are indexed by rank of the matrix. Two matrices will be in the same orbit if they have the same rank, same number of linearly independent columns. That's what's going on here. In contrast, if I had put PA P inverse, then the equivalence classes would have been equivalence classes of similar matrices, and there you would have had to use the real Jordan form. That would have been a representative for each class, and your conjugation action would move around matrices which have the same real Jordan form. I think everybody understands this problem. I'm not going to waste, we've talked about this. And then finally, problem 7, I said, state the class equation and explain how it is derived. This was ignored by about half of the class because of time, I'm sure. That's fine, I understand, there's a lot going on. But that's basically just it, the thing I was looking for here mostly is that you mentioned that we're looking at the group action of conjugation, right? And then, of course, the class equation, which is that the size of the group is the order of the center plus the sum over the non-singleton conjugacy classes, right? So if you told me that it was from the previous problem that the fixer is the center, right? And that the action was conjugation, I was pretty happy with your solution. Any questions? I'll try to make the next test a little bit longer. No? No? This is good length?
Just a
It
little
was better.
A little short.
It was still kind of long, but
Close.
I feel like I'd like to grade a test that's only a page long. That would be easier for me.